Hello, and welcome to this next instalment of the Micromeritics webinar series. My name's Stimpson, and today we'll be examining single and multivariate approaches to powder testing, with a particular focus on tableting and dye filling operations. Both single variable and multivariate testing schemes offer pros and cons depending on the system under investigation. When posing the question, does an increased sugar intake lead to poorer health outcomes, then simply comparing the quantity of sugar consumed against the health of individuals is a reasonable methodology to adopt. However, when attempting to make predictions of the weather on a given day, solely examining atmospheric pressure, for example, may lead to incomplete or misleading results. Conversely, when investigating sugar-related health outcomes, it may obscure the results to also consider the fat content of foods, pre-existing health conditions, and the effects of other ingredients. The results may not be incorrect, but they may be overcomplicated in terms of interpretation and dissemination. It's therefore important that we're able to assess not only the system we're attempting to measure, but also to consider what we want to learn and how we hope to understand our data. As seen in the previous example, single variable analysis is most effective where direct links exist between that which is measured and that which it is thought to affect. In powder processing, this might be a link between particle size distribution and packing efficiency, for example. However, where such links exist, it's important that the relevance of these correlations are not overextended. Just because PSD influences packing efficiency, it may not correlate in the same way in downstream processes, for example, or if powder properties are heavily altered during processes. Multivariate testing relies on the acquisition of multiple data, either by examining multiple properties of a sample or by running different types of testing. This approach is particularly strong where the details of links between sample properties and the resulting product properties are poorly understood, either from complex processing or a lack of physical and chemical understanding of the sample and processes. It's easy to see how users might balk at such an approach, as the learning curve may be steeper and the resulting data may be more difficult to interpret. However, as we'll see, this is not always the case, and in fact, multivariate approaches may be easier to interpret and more efficient in terms of applying data to problems and acquiring solutions. Single variable testing may be faster and have simpler conclusions with strong correlations between powder properties and process parameters, whilst requiring smaller samples. However, only narrow elements of process rationalization may be found, and important or useful information may be missed, or worse, incorrect conclusions may be drawn. Meanwhile, multivariate testing unlocks a wide range of data which can allow all elements of a given process to be rationalized, whilst allowing for the generation of robust acceptance criteria and informing about physical powder characteristics, and even providing information which was not part of the initial experimental goals. However, depending on the system being investigated, it may be slower than single variable approaches and require greater quantities of sample. To compare the two approaches, we'll look at a pair of case studies. Both of these studies can be seen as successful applications of their respective approaches, but we'll consider whether or not one method might be more useful than the other. Firstly, let's take a look at wet granulation for tablet manufacture, which attempts to link a single rheological property to the final product quality of a pharmaceutical tablet. Granulation is favored in many powder processing environments for its value in improving the handling properties of otherwise hard-to-process powders. Further to this, by reducing segregation and thus improving the uniformity of final products, it can have a beneficial effect on ultimate product quality, as well as preserving safety and cleanliness in process environments by reducing dusting. One granulation method sees the introduction of water to powder during high shear blending. Here, the water quantity and addition rate, impeller and screw speeds, powder feed rate and granulation time all have an impact on the flow properties of the resulting granules. However, the purpose of this case study was to establish if those flow properties can be used to predict the final hardness of the tablets for which the granules are intended. If so, then a single sampling point and flow property might be used to set process parameters to obtain a specific desired tablet hardness, which is a useful goal. Here we can see a typical tablet production system comprised of a number of different discrete processes. It's easy to see that, due to the intense processing a particular powder will endure, the powder properties may change a number of times from beginning to end, so sampling at the correct stage in the process will be important. In this study, granules in both wet and dry condition were tested, with any link to the final tablet hardness identified. In a typical granulator, water content, screw speed, powder feed rate and barrel temperature are usually configurable. Geometries may vary from manufacturer to manufacturer, but these factors are usually common between variations. Integrated or separate dryers are usually variable in terms of drying time, air velocity and air temperature, but for this study, only the granulator parameters were varied. Although two formulations, APAP and DCP, were used for this study, it is the process variables which are most relevant. Here, the water content was varied between limits set by visual inspection, i.e. if the water content was seen to produce overly wet granules, then that water content setting was not investigated. Only water contents which resulted in a useful granule quality were used. 3 screw speeds and a number of powder feed rates were also used. It's important to use a number of granulator settings so that granules of different flow properties can be achieved, as the granule flowability is the variable we want to correlate with final tablet hardness. In order to establish the flowability of the granules produced, the flow energy of each powder was determined by powder rheology, with the force and torque incident on a blade passing through the powder being used to determine the powder's resistance to flow. High values of flow energy correspond to a powder which is more resistant to confined flow. However, it should be noted that high or low flow energy should not be assumed to be good or bad. The specific process involved may require one or the other condition. For the purposes of this study, the flow energy is simply intended as a predictor of final tablet quality, and the relative flowability in a particular element of the process is not under investigation. First then, we can see the effects of different screw speeds on the impact brought by varied water content. Where we intend to vary the basic flowability energy, or BFE, a strong response to changes in water content is desirable. Remember that we want to use BFE to determine our final tablet hardness, so greater sensitivity to the water content makes that easier. Here we see that a slower screw speed means that the changes in BFE are more pronounced when changing the quantity of water, so control over BFE is easier when employing a slower screw speed. Next we can see the effect of varying both powder feed rate and water content. This shows that there may be multiple routes to a given BFE, so if we want a faster process without sacrificing BFE, we can achieve this by moderating the water content. This shows us that if we do see a correlation between BFE and tablet hardness as intended, then we can use whatever recipe we like to prepare our granules, provided it achieves the appropriate BFE, allowing us to fine-tune the efficiency of our process. Here we have chosen 4 different recipes or conditions, with the various process parameters used to create them in the top graph. We have then sampled each of the recipes at 4 different stages in the granulation process. What we see is that the differences between each condition are more or less pronounced, depending on which part of the process we are sampling. Directly after wet granulation, we see that condition 1 and 2 produce very similar BFEs, as do conditions 3 and 4, although the 2 pairs are widely separated. After the drying stage, though, each of the 4 conditions produces significantly different BFE values. This means that if we are targeting a specific BFE, this would be an advantageous sampling point. If we sample after the milling stage, we can see that the measured BFEs are a little closer together, and after the lubrication stage, they are almost indistinguishable. So now we know that if we find a correlation between granule BFE and tablet hardness, then the best point to sample our granules to measure their BFEs is after the drying stage, where there is a good differentiation between each recipe. Of course, all of this hinges on there being a good correlation between the BFE and tablet hardness. So let's take a look at those results next. The tablets were produced in a common tablet press and then measured in a common tablet hardness tester. Each coloured series on this graph corresponds to each of the different sampling points shown earlier, with the gradient of the line indicating the strength of the differentiation between recipes, with a shallower gradient showing greater sensitivity to changes in BFE. As we can see, there are strong correlations between BFE and tablet hardness at each sampling point. However, were we to sample at the lubrication point, for example, even a small difference in BFE could have a significant effect on the resulting tablet hardness, making it much harder to control the product quality. By contrast, sampling the granules after drying means that small differences in BFE have only a small effect on the tablet hardness. So if we want to target, let's say, a tablet hardness of 10 kPa, then we will require a BFE of around 3,300 millijoules in our dried granules. If we achieve 3,200 or 3,400, our tablet hardness is still likely to be close to our target. So, we were able to see a strong correlation between a single powder property and our final tablet quality, which is great. However, was the testing scheme we used the best for that process? We can speculate as to why BFE is linked to tablet hardness, most likely because the flow energy of a powder tends to rise with packing efficiency, and an efficiently packed powder is less likely to contain weaknesses and defects when it comes to the compression stage. However, it's not necessary for us to understand the physical mechanisms involved. We have identified a good sampling point, and we've been able to use a single test result from that sample point to predict our tablet hardness. Goal achieved. However, we still had to do a large amount of testing and had to vary a large number of process parameters. The data was also more complex to interpret than might have been expected, and although we can speculate as to the physical phenomena involved, we have no real idea whether or not our speculations are accurate. Lastly, we only really know that this predictive method is useful for the specific formulation involved. If we want to use this method for other materials, we will have to repeat our entire process for that specific formulation. Our next case study looks at multivariate testing of a dye filling process in tablet manufacture. While such processes are indeed common in pharmaceutical applications, similar methods are employed across powder handling industries, and the lessons learned can be widely applied. A typical tableting process involves delivering a powder to a feeder and the filling of a tablet dye, followed by initial compression, compaction, and finally the ejection of the finished product. However, this case study focuses solely on the filling of the dye itself. It can be assumed that for most tablet making processes, a full dye is a good dye, with consistent, uniform filling and low air entrainment being beneficial. Porous, partially filled dyes will result in significant weight variations between tablets and between batches, and poor quality tablets which may break via capping or lamination effects. Where pharmaceutical tablets are concerned, these issues don't only look bad and lead to poor experiences, but due to the use of drugs, they can have serious results for the end user. So obtaining good quality dye filling is of critical importance. There are a number of powder properties which can lead to poor dye filling. Namely, these are high interparticle cohesion, which can lead to inconsistent flow into the dye. Also, high levels of friction and mechanical interlocking between particles can cause cap-like structures to form, preventing the flow of powder into the dye altogether, or trapping air, which leads to poor compression properties in the subsequent processing steps. Lastly, if air is trapped in the dye, poor permeability can prevent that air from escaping, leading to a partially filled die with all the associated complications. Each of these properties will be measured in order to define the acceptable limits for any powder intended for use in a given die filling process. The cohesion of each powder will be measured by investigating the sample's aerated energies. In this test, the flow energy of powders under increasing levels of aeration are measured, with the minimum flow energy considered as an indicator of the strength of the cohesive forces between particles. Powders with low aerated energies tend to flow more consistently under low consolidating stresses, whilst more cohesive powders, i.e. those with high minimum aerated energies, tend to flow more inconsistently. Specific energy is a measurement of friction and mechanical interlocking between particles, which in turn determines the likelihood of structure formation during the die filling process. Effective die filling depends on low structure formation and therefore low specific energy values. Finally, the permeability of the samples was measured by passing air through each powder under increasing compressive stress. As the resistance to airflow is what's being measured, powders exhibiting high pressure drop values are considered less permeable, while samples with low pressure drops are considered more permeable, allowing any trapped air to escape during the die filling process. For this study, 4 different powders were chosen to provide a range of different properties. 2 sizes of glass beads and 2 metal powders gave a good range of size, shape and surface texture. It should be noticed that the goal here isn't to assess these powders for their suitability in the die filling. Rather, the intention is to define the limits of powder properties that will work well in the process. Here, the powders are unimportant. It is the testing procedures which we hope to define. An ideal filling process will result in a high filling ratio, i.e. a full die has a filling ratio of 1, whilst an empty die will have a filling ratio of 0. It can be seen here that all powders present filling ratios of about 0.8 or higher, provided that the shoe speed, how fast we're filling the die, is kept low. However, if processes are intended to be efficient, then a high filling shoe speed is important. We can see then that only the large glass beads retain a high filling ratio at these speeds, whereas the other powders all result in a die which is less than half full. With that in mind, we will consider only those results from the 200 millimeters a second filling speed. Firstly, let's take the high-speed filling ratios and compare these to the aerated energy from each sample. We can see that the small glass beads, aluminium powder and large glass beads all fall to a minimum aerated energy around 0 millijoules. The titanium powder, meanwhile, has a minimum aerated energy of around 300 millijoules. From this then, we can see that an energy below this can be seen as good, whilst higher energy is bad. By itself though, this test isn't sufficient to rationalise our process behaviour. We can then add our specific energy values. We can see here then that the large glass beads, our best performer, are not the lowest in terms of specific energy. As the aluminium and tungsten are both greater in specific energy, then we can be confident that the upper threshold lies somewhere in between the large glass beads and the aluminium. Anything above this threshold is likely to perform poorly, whilst anything below it should behave well. However, even using both of these tests, both the large and small glass beads seem to pass, even though we know only the large glass beads maintain a high filling ratio. So, the aeration test allowed us to exclude more cohesive materials like the tungsten, but didn't differentiate between less cohesive samples. Our specific energy allowed us to find a maximum threshold for mechanical interlocking and friction, but wasn't able to differentiate between our two kinds of glass beads, although it was able to show that the aluminium powder was too frictional for our process. Not until we add in our permeability results that we are able to see that the smaller glass beads are simply too impermeable to allow any trapped air, even if it is a small amount, to escape from our die during filling. More than that though, we can see that no individual test singles out one powder as acceptable. By itself, each test would have allowed a poor performing powder to be accepted too. In that case, we need to apply some criteria if we are to use these test procedures as a predictive model. Remember that we don't want to make tablets out of glass beads or metal powders. We just want a test which will allow us to predict whether a given powder that we're making tablets from will behave favourably in our process. We know that we want low cohesion to give us a consistent flow into the die, and that we want moderate or lower interlocking and friction between particles. And lastly, we know that we want a highly permeable powder so that any air which is trapped during the filling process can escape, leaving all the available space for our powder. When we apply these criteria to our graphs, it's much easier to see how our model can be used. Only a powder which fulfills each of our criteria will be acceptable. A failure on any single test, such as excessive friction in the aluminium or too little permeability in the small glass beads, highlights a powder as unacceptable. Only a powder which passes all three tests is likely to give us a suitable filling ratio. We now have a set of tests and a range of acceptance criteria which we can use to screen any proposed new powders for acceptability, and we can also infer the reasons any rejected powder might not be suitable. So, was this multivariate approach easier or more burdensome than the single variable option? And was it more or less effective? In fact, the amount of testing required was similar in both applications, but in the multivariate approach, we can use our model as a predictive tool, meaning that we only need to run each one of the three tests for any incoming sample. So in the long term, it may be less burdensome. We can also see that we can begin to infer some idea of the physical phenomena which are impacting our processes. By viewing the results from each test as a whole, we can see the impact of the physical parameters of the powders on their behaviours, at least in some small way. It's also possible that we could use some of the data gained in these tests to assess other aspects of the tableting process. For example, we may be able to correlate the trapping of air encouraged by high specific energy with poor performance in the subsequent compression step. However, the correlations aren't as mathematically clear as they were in the single variable approach, and the limits on each of these three parameters isn't concrete. Further testing might be necessary to really nail down the hard maximum values of each property. Lastly, the material properties of the powders certainly weren't essential in determining our criteria, but they were useful when trying to understand exactly what was taking place and why. Which approach should be chosen for a given investigation then? Well, if looking for strong correlations with simple understanding, where we're not concerned with predictive capabilities or a physical understanding of the systems involved, then perhaps a single variable approach is best. If we're not worried about a solid correlation, but would like to just see useful results and learn about our powders in a phenomenological sense, then perhaps multivariate is best. Of course, there is one point which is worth raising here. Maybe we can just combine the approaches of both systems by measuring a few more flow properties so that we gain a fuller understanding of the system. Well, we can, yes, which basically means we're just using a multivariate approach. So should we just take the multivariate approach all the time? Unless we have a specific need to conserve powder and we have real restrictions on the testing time available, it's always worth considering a multivariate approach. It can give us a better understanding of our processes, and we may learn extra nuggets of information that we didn't initially expect. We can learn about the physical limitations imposed by the properties of our powders, which can inform both our future testing and processing decisions, leading to less work and greater efficiency down the line. In most cases, we're not really sacrificing testing time as long as we're thoughtfully applying our data, so it's worth taking the extra steps in order to extract the most from our work. And finally, we can develop predictive models which can be used to greatly reduce the necessity for complex investigations in the future, lowering our dependence on testing, expertise, and samples. Thanks very much for listening to my webinar today. I hope you found it interesting, and I hope you'll come back for more micromeritics webinars in the future.